So good evening, or depending on where you're joining from, whatever part of the day I should refer to. So welcome to the first invited talk. Speaker is going to be Professor Peter Bürgisser from the Technical University of Berlin. Peter obtained his PhD from the University of Constance. Then he did his postdoc in the University of Bonn and then at Zurich. He was then a professor at the University of Paderborn and has been with TU Berlin since 2013. So Peter is an expert in almost all aspects of algebraic computation, and he has done foundational work in the field of algebraic complexity theory, geometric complexity theory, etc. Among his many beautiful results is this recent swath of results that sort of give very analytic solutions to problems that are typically quite algebraic in nature by exploiting invariant theory, convex optimization, and etc. And he is going to tell us a bit about some of these connections in some of his recent work. Yeah, over to you, Peter.
Okay, thank you very much, Ramprasad, for the very nice introduction. I'm happy to speak here, to being able to present these new ideas, these developments. So I think I should share my screen. Okay. I hope you can see it. Okay. So
yes, it's visible.
Okay. So my talk is mainly based on joint work with Cole Franks, Anki Garg, Rafael Oliveira, Michael Walter, and Avi Victorson. So we have been working on this problem for quite some time, and we had several publications in conferences. So far, no journal publication, but we are working on it. Actually, it's becoming a long work. It's about 100 pages, and I hope we will have an update on the archive in a month or so. Okay, what is very exciting about this, and I think Avi Victorson, he gave many talks about that as well, is these manifold connections between disparate areas. It's quite amazing. Never in my life I have worked in an area where there are so many connections. So I think it's very exciting and rewarding. Okay, so let me start with motivation and background. So where are my origins? So my origins, algebraic complexity theory. And actually the topic of the talk is in some way connected to it. So there is this famous question from going back to Les Valiant from 1979, where he asked whether one can compute the permanent of an n by n matrix with a number of arithmetic operations polynomially bounded in n. Okay, and as most of you probably know, this led to a beautiful theory, the theory of VNP completeness, which is quite analogous to the PNP question, but in this framework of computations polynomials. And there is this, I would say, holy grail of algebraic complexity theory, which is the question whether the classes VP and VNP are equal or not. Okay. On the other hand, there's a completely different problem, which is the Derandomization or polynomial identity problem, which at first glance looks completely unrelated. Most of you know that, of course, and even there are many specialists on that in the audience, I'm sure. So what's that? So you are given a polynomial by an arithmetic circuit, maybe in some restricted model, and then you want to decide in deterministic polynomial time whether this polynomial is the zero polynomial. It's clear that when you are allowed to do randomization, you can do this in an efficient way, but can we avoid the randomization? So very amazingly, I mean, these two problems of proving lower complexity bounds and de-randomization are closely connected. There is this very well-known paper by Impagliazzo and Cabanets from 2004, where he showed that the questions are closely related. I don't want to state it formally, but I'm sure many of you know. So, okay. So anyway, people realized one way to prove complexity lower bounds is maybe to de-randomize. Okay, this polynomial identity testing question can be phrased in a much more concrete way as follows. So this is sometimes called symbolic determinant identity test. So it's the following question, very concrete. You are given, maybe I should use my pointer. Okay, try it. I have n by n matrices, A1 up to AM, okay? Then I form a formal linear combination with variables xi, okay? And I ask whether the resulting symbolic matrix is the zero matrix or not. Okay, you may also think of a matrix where the entries are linear forms in the variables. So Edmonds, like in a pioneering work very, very long ago, he asked whether this can be done in deterministic polynomial time, and he solved a special case in it. And by a reduction due to Valiant, the PIT is essentially equivalent to this question. Okay, essentially, okay. So these are motivations. So, and interestingly, these questions that I explained to you, that somehow they are all related to, they have seen progress using invariant theory. Okay, so why invariant theory? I mean, the first researcher who looked into that was Volker Strassen, my PhD advisor. So he did pioneering work where he linked computational complexity, algebraic geometry, and he also thought about the representations and invariants. Okay, but then it was further developed by work by Ketan Malmalay. He made this connection to clearer in a series of papers, and he coined for it the name geometric complexity theory. And basically what he did, I mean, he asked, he has many conjectures, and many have been disproved, but it's a very nice source of ideas. So among other things, what he did, he rephrased this VP, this famous VP-VNP question as an orbiclosure problem. Okay, so then you have the connection. Okay. On the other hand, there is a recent paper by Garg, Gurwitz, Oliveira, Victorson, my co-authors, so from 2016, where they solved the non-commutative polynomial identity testing problem. So this is exactly the problem that I had on the previous slide, symbolic determinant identity test when the variables are non-commutative. Of course, one has to discuss what this means, what is the determinant, etc. But it's essentially this problem. And they solved it. And a crucial ingredient of their proof was invariant theory. So that's how these people entered invariant theory. I would say I came like from a different side. Okay, so what is this invariant theory? What is it all about? Okay, it's something, it's a part of mathematics that is quite old. I mean, you study quantities that are conserved under the action of a group. So this is clearly also something that is very of high relevance in physics. It's kind of a guiding principles in physics, preservation of energy, preservation of momentum, etc., etc., etc. Okay, and in the 19th century, invariant theory was a major topic in algebra. So you can see all these names, Cayley, Sylvester, blah, blah, blah. I don't have to read all of them to you, but all of these people made contributions. So it was very fashionable that time. Okay, so I will now, talk a little bit about geometric invariant theory and then also formulate more precisely the problems we are studying. So geometric invariant theory. Okay, so this slide is again very general. I wanted my talk to be comprehensive. So as I said, symmetries and group actions, we know in mathematics, symmetries are formalized by the action of groups. So this is extremely general. If you want to explain to anybody in the street, what is it? You can say, okay, we have the group of rotations, you have some object, you rotate here an object, here another object. Okay, you want to tell, is it the same object? Okay, so can you from one object go to the other by your rotation, maybe also translation? Okay, then so configurations that arise by rotation, say, will be considered equivalent. So this is this very general equivalent problem. Okay, that's actually a problem I'm interested in. I want to determine whether two given objects are equivalent or maybe approximately equivalent. Maybe there are errors and so on. Okay. So this is still very vague, but as a computer scientist, we will surely recognize here as a special case, the graph isomorphism problem. Okay, so here is everybody knows the graph isomorphism problem. Okay. Okay, but I'm not so much interested in the discrete problems. I'm more interested in continuous problems. Okay. Okay, so now this slide is a bit more formal now, so I try to give definitions, but without being too formal. So let me explain what is the orbiclosure intersection problem. So there will be many examples, so don't worry, but I have to fix the scene. So I have a complex vector space V, finite dimensional, like C to the M. And then I have a group acting on this vector space. Usually this group is infinite. So I don't think of finite groups. Usually it's infinite connected. Okay. So then I say two vectors are equivalent if I can say, I have V1 and V2. Okay. If I can reach V2 starting from V1 by applying a group element. This is the question. This is the equivalence problem. And I define the orbit. Okay, I denote it by GV. It's just the equivalence class of V. So the set of all vectors that I can reach by applying group elements. And the equivalence problem is this: given two vectors, are they equivalent? Okay. And then you can study this maybe in the Turing model of computation. You assume the coordinates of the vectors are, given by rational numbers, etc. And so on. But you can also look at it more numerically. Maybe these vectors are not given exactly. Maybe there is some error in it. Okay, then it makes more sense to look. I mean, this equivalence problem maybe is not so meaningful anymore in the presence of errors. So maybe you would rather ask whether these two orbits are close in a certain sense. And if you think about it after some time, you realize that the right way to formalize it is as follows. So you look at the orbit closure. So you have this orbit, and then you take its closure with respect to Zariski topology. So all the vectors in the orbits and all those that can be obtained as a limit of a sequence of vectors in the orbit. Okay. And then I phrase the orbit closure intersection problem, which I see as a robust version of the orbit equality problem. This is the main problem I'm interested in. So given two vectors, V1 and V2, here, do the corresponding orbit closures intersect, yes or no? Okay, because this is completely general. Okay, and actually this problem is also very difficult in that so far we don't have so many general results. I mean, we are on it, but so I think, but we have already quite a number of insights on a special case of this problem where we know we have to solve first. And this is the next problem. Okay, this is called the null membership problem. So now I assume that one of the two vectors is 0. Of course, the orbit of 0 is 0, the orbit closure is 0. So this orbit closure intersection problem translates to the following question, given a vector V. Okay, then you look at the orbit closure of V and you ask whether the 0 is in that. So it looks maybe a little bit artificial when you see it for the first time, but it's not that artificial. So why is it called null membership? Okay, I didn't fit the slides, but the set of vectors V with the property that this holds is called the null cone, and it was introduced by Hilbert around the turn of the century. In Germany, it's Nullkegel. So this is this problem. Okay, so there is a related problem. This can be very confusing. Okay, the orbit closure containment problem I discussed with Marcus. Okay, what is this? You have here, I'm here. You have two vectors, V1 and V2. Now you ask, is one orbit closure contained in the other? Looks quite similar than the other one. And this is the problem that is highly relevant for geometric complexity theory. So actually this VP versus VNP problem, you can rephrase as such a problem. Also the complexity of matrix multiplication, you can rephrase. So this is an important problem for complexity theory. There has this geometric complexity. The GCT program tries to resolve this, and there was, as you probably know, there was a suggestion by Ketan Malmalay that one should do it using occurrence abstractions. Now this is just in some joint work with Christian Nickemeyer and Greta Panova. Actually, we could prove that this is not possible to do it this way. Okay, but this is just a advertising of some result that is maybe not too closely related to my talk, okay, but I wanted to mention it anyway. Okay, so there's a nice insight by Marcus and co-authors. So And he proved that actually this orbit closure containment problem in general is NP hard. Okay, maybe this is expected, but it was very hard to prove. I mean, it's very hard to deal with these orbit closures. And so they came up with a setting where you actually could prove it's NP hard. Okay. So, and I think this is very interesting. I think it's very interesting because I believe that this orbit closure intersection problem is of a very different nature. Maybe, I don't know, 10 years ago, I would have thought that it's NP hard, there is no hope. But now I don't think so. I rather believe that this is doable, you know, as polynomial time algorithms. We don't know that yet, but we have already found efficient algorithms in several special cases, which I think is very exciting. Some of these algorithms are based on algebra, but some of these algorithms, and maybe the most promising ones, are based on numerical computations, actually optimization over non-commutative groups. Okay, and this brings us to the title of the talk. Okay, so I give now one example so that you are, I hope you will not be completely lost. This is a beautiful example that it's a baby example, but it explains many of these notions. Okay, so the vector space V is a space of complex n by n matrices. Okay, then the group is GLNC, so group of invertible n by n matrices, and the action is conjugation. So this is the action that we learn in linear algebra in the first year. In German, it's called, okay, similarity, I think it's called. Okay, so and then, right, so you have two matrices, A and B. You wonder, are they the same orbit or not? And then we learn in the linear algebra class, and usually it's the hardest theorem in the whole class. Well, this is the case if and only if they have the same Jordan normal form. So the answer is a bit tricky. Okay. Now, how about this orbit closure intersection? Okay. So that's actually the answer to that is simpler. Okay. It takes a little bit time to figure out. But actually, the answer is this. The orbit closure of the matrices A and P intersect if and only if A and P have the same spectrum, counted with multiplicities. So it's the question. Okay, this actually, you see, in a way, the second problem is easier, in a way, has an easier solution, and it is very meaningful. Okay, and this is the type of question that I want to investigate, but in larger generality than just for one matrix. Okay, so let's see, what is this null cone? The null cone, well, now consists of all those matrices where all the eigenvalues are 0. So these are the nilpotent matrices. Okay, the null cone is a set of nilpotent matrices. Here you can also see the nature of the null cone. It's kind of the degenerate object, if you want. The objects, they are like 0, but not 0, but they are like 0. And usually you don't like them, but you have to deal with them somehow. Okay. More about invariant theory. So what are invariants at all? An invariant is a function, okay, defined on my vector space, taking complex values, that is constant on orbits. Okay, invariant under the group action. Now, clearly these invariants, they form a ring. I mean, the sum of invariants is again one, the product, the difference, etc. So they form a ring. And I will focus on invariants that are polynomial functions, okay? Also, let's assume now that our group is reductive, and whatever this means, think of GLN, okay? So this, what I'm going to tell you doesn't work for all groups, but say for many, many groups. Okay, so Hilbert, at 1890, he wrote, he wrote 2 papers that were very influential, actually the starting point of modern algebraic geometry. And in this paper, but it was about invariant theory, and one of the theorems he proved was this. It's his fineness theorem. He proved that for GLN, that this ring of polynomial invariants has a finite system of generators, finite, okay? And also, I mean, it comes out that when does a vector V lie in the null cone? Well, this is the case if and only if V is a 0 of all invariants that are not constant. I mean, because you have to exclude the constant one. Okay. So the null cone is the zero set of all non-constant invariants. Let's check this theorem in the example of the conjugation to get a little bit of a feeling what this could mean. Okay, let's go back to conjugation of matrices. Okay. So, right, what you can do, you look at the characteristic polynomial. So my t here is just a symbolic variable. I take t times identity matrix plus a, the determinant, then I expand this. Okay, then the coefficients are functions of the matrices. Clearly, among those coefficients, I find the trace, I find the determinant, but other ones. Because the characteristic polynomial is an invariant under conjugation, all these fi are invariants. And one can prove, it's not too hard, they generate this ring of invariants. Okay. And then you see, now it's okay. Right. So for which matrices A do all invariants vanish? Well, this is when this whole thing is not there. So the characteristic polynomial is t to the n, and this is exactly the case for the nilpotent matrices. Okay. I hope now you got a little bit of a feeling for these notions. Right. So everybody knows this for conjugation of one matrix, but what happens? Okay, I'm going too fast. There's another thing I wanted to tell you, important. Now, geometric invariant theory, there was a paper, an important development by David Mumford, 1965. He further developed this theory. He created geometric invariant theory. And one of the things he proved was this. Actually, he said, okay, I can characterize, I'm in the setting from before, and he can characterize this, that the orbiclosures of V1 and V2 intersect. This just means that for all invariants, V1 and V2 take the same value. Now it's clear that one direction is, of course, clear. I mean, this direction is clear, okay? Because invariants are continuous. They are constant on orbiclosures. So if there is a common point of these two orbiclosures, clearly I must have the same value. And it's not, I mean, the other direction, it requires proof. Okay, now this theorem, okay, immediately suggests an algorithmic solution. I mean, Hilbert said there is a finite system of invariants, so one could think of just taking a generating system of invariants. It's there, it's finite, and just test this, okay? Okay, so it's, in a way, it shows it's decidable, okay? But maybe not much more. I mean, there are many problems with this idea, okay? It may not lead to efficient algorithms. I mean, the number of invariants, it may be huge. We know in examples it can be huge. The degree may be huge. We know that it may happen. Or even if there are not many and the degree is not very high, it may even be the case that you have some guys there that are just hard to evaluate, okay? So it doesn't look so easy. So Ketan Malmalay, he had observed, he had studied several examples, and then he suggested some way out of it. I'm not going into the details, but he suggested the existence of certain succinct encodings of generators for solving this problem. And I mean, if his hypotheses were right, as a consequence, you will get polynomial time algorithms for orbiclosure intersection problem. So unfortunately, this conjecture was not true. It was recently disproved by a long list of people, our friends. Okay, it doesn't, again, as usual with Ketan, it doesn't mean it's completely finished. You can modify this a little bit, and then the question is again open, right? But it's maybe not clear that we should approach this problem this algebraic way. So maybe we should try something else, okay, numerically. Okay, how is my time? Okay, more or less okay. So let me now discuss a class of examples that is more involved and already led to this very impressive applications for the derandomization. It's the left-right action on matrices. Okay, the setting of left-right action of matrices. So what do I have here? My vector space consists of m tuples of n by n complex matrices. Okay, and the group is SLN times SLN. So recall SLN is just a group of matrices of determinant 1. And the action is simultaneous action from the left and from the right. So it's defined here. You can also think of simultaneous manipulation of the rows and the columns, if you like that better. Okay. So this is the definition. And it's if m equals 1 is completely clear. I mean, the normal forms is given by the rank. Okay, good. But if now we have more matrices. So we try to understand invariants. So, I mean, one obvious thing is you take your matrices, you form a linear combination with complex numbers and take the determinant. This is clearly, okay, this must be an invariant. So one may hope that maybe these already generate the ring of invariants, which is true for m equals 2, but not for m greater than 2. Okay, there you need more. Okay, right. But you don't have to do so much more to come up with specific invariants. Namely, the idea is this. Instead, these coefficients, the lambdas, let's take matrices. Let's fix some d. And take coefficient matrices, which I denote capital lambda. Okay, and then I form this linear combination, but of course it will not be a scalar multiplication, it's a tensor product. Okay, I can still do that. Okay, if the matrices get much bigger, I take the determinant. Now it's an easy exercise to prove that this will as well be an invariant. Okay, right. Okay, and there is a result from algebra, which is 20 years old, which says that this way you get the whole ring of invariants if you allow for any d. So you can list the, I mean, these people discovered it more or less independently and in more generality in the quiver setting. Okay. Right. So what can we, so, okay, in what sense is this now useful? Okay, we get some description of the null cone, but we see it's quite complicated. So the Hilbert said, okay, null cone consists of the zeros of all of these invariants. So I can say now a tuple of matrices A1 or to AM is in the null cone of this left-right action, if and only if for all D and for all coefficient matrix lambda, this linear combination is singular. Okay, is singular. Okay, right. Now comes a difficult step. Okay, I don't have much time. I want to, okay, what I want to do. Okay, I want in a way replace these coefficient matrices by variables, by non-commutative variables. Okay, so I want to interpret this here as statements in an algebraic domain, which is not commutative, but in the most general sense. And one can do that, but I have no time to go into that. There is this notion of the free skew field, which is written in this funny way. So the xi denote non-commutating variables. So maybe it's easy to understand what's going on if you don't think of field, but just non-commutative polynomial ring, maybe. Okay. Right. And so actually this star here means the singularity of this matrix here. So if this linear combination of the matrices where the variables are non-commutative. So it's like the Edmonds problem, but a non-commutative version. Okay, so there is a whole book by Kohn, PM Kohn, where he explains all that. Okay, right. So what can we say about this problem, how hard it is? Well, I mean, if this is everything you know, it's not even clear that it's decidable, but fortunately there are bounds on the degree. So there was a very general degree bound by Harm-Derksen, for completely general for invariants. And by this, he says, it's enough to look at matrices of size d, which is exponential in n. So once you have this, right, I mean, you get some algorithms, but maybe not efficient, okay? Okay, so now the amazing thing is, right, so again, is this question, I write it again. This question has a deterministic polynomial time algorithm. Very surprising, very it looks at first glance, you would think this problem is harder than the commutative case, but it is not. There is a deterministic polynomial tile algorithm for the non-commutative version of the Edmonds problem, and this is in the paper by Gar, Kurwitz, Oliveira, Victorson from 2016, which I think is very important for starting all these investigations. And this proof it was also very surprising. This proof is non-algebraic. It's by a numerical algorithm. Actually, it's called operator scaling. I don't have time to explain exactly what this is, unfortunately, but it's an algorithm that is very easy to describe, but kind of hard to analyze. Okay. Then I should say that, well, I mean, it was not even clear that you have a randomized polynomial time algorithm, but roughly at the same time as when this paper came out, Derksen and Makam, they improved this degree bound by Derksen, and they proved this bound is sufficient. Okay, so once you have such a bound, then it's easy to see there are randomized polynomial time algorithms. And then there are more papers. I mean, there have been many papers here. It has been investigated very quickly and at great depth. Then Kiao, Subranayan, and Ivanios, they found algebraic algorithms for this problem. So if the other one is numeric, but this is algebraic, also polynomial time, it even works over any field. Okay. You can even do the orbit closure intersection problem with indeterministic polynomial time, but I'm, since it's not the main focus of my talk, I don't enter this. So we know a lot about this left-right action, and this is non-trivial, okay? But we have a lot of positive, surprising results. Now, if you go to tensors, the situation is a bit different. Okay, this is my only slide about tensors with the hopefully nice picture. So what is a tensor? I mean, matrices organize your data in a two-dimensional way. Now, tensors of order 3 organize it in a three-dimensional way. Everybody knows. The elements, if you like indexes, is it such a three-dimensional matrix? But you can also think of it more abstractly as an element of this tensor product. Okay, tensors appear almost everywhere. Okay, they are also very important in data analysis. Okay, so it's quite fashionable to work on tensors. They're important in quantum information theory, they entangle qubits, and so on and so on. So what's the connection to before? So yeah, okay. So if you look here, think of like a three-dimensional matrix. You have like the third coordinate direction is like a distinguished one, and then you describe your tensor as just by the slices. So then you have n quadratic matrices. These are the slices. Okay, that's what I studied before. Okay, now if I say, okay, I want to have an action also on these slices, I also want to an action on this vector space. So the group is now SLN times a third SLN. Then this is called the tensor action. Okay, and that's very important for complexity theory, etc. Many areas, but it's much harder. So okay, so we don't have these nice results as for the left-right action here. Many open questions. So for instance, we don't know whether null-com membership works in polynomial time for tensor action. Okay, so what's my time? Right, okay, a little bit. So now, okay, it's the last part of my talk. Now, actually, I will explain you a little bit what is in this joint paper, which is the main basis of my extended abstract, and there will be the new results. So let me report and summarize a little bit what's in that long paper. Actually, I don't have, my time is limited. So I thought I will just start with the summary. Otherwise, in case there is not enough time. So what we do, so we are in this very general setting. So one feature of this paper is it's extremely general. Okay, as general as you want. Reductive group acting quantum space, blah, blah, blah. And then what we do, we develop geodesic methods for optimization. I will explain in more detail what I mean. We have a first order and the second order method, which are modeled after what people do usually in Euclidean optimization. And so we get algorithms that basically, and results that basically unify everything that was done before. Okay, and the problems we look at is norm minimization and scaling, which I will explain. So in particular, we get back the results on metering scaling and operator scaling. And what we also do, we analyze these algorithms. We have identified the key parameters which control the convergence and complexity. Okay. So again, we get deterministic polytime for null-com membership in many settings. I mean, in all the cases we had before, but in a few more, but we don't get it for tensor action. And there is this list, like maybe it's just amazing, all these connections and applications, but my time is a bit limited, so maybe I will not enter this. But if you go to the extended abstract, basically by this extended abstract is basically the introduction to the long paper, a little bit, a little bit adapted. There you will see more information about all these surprising connections. Okay. So it's not just an esoteric thing, it has many, many connections. So now let me explain what kind of optimization. So we go back to the general setting, the geometric setting, our group acting on the vector space. Okay. So probably it's best to think of GLN. GLN has this compact subgroup K of the unitary matrices, but it also works in more generality. You take a maximal compact subgroup K, whatever it is, okay? Then I assume that on my vector space V here, well, I can always choose a Hermitian inner product with the property that the action of these elements in K, let's say unitary action, acts isometrically. This I can always assume, and I will assume it, okay? So then, what is this norm minimization? So this is my favorite naive picture. I have my vector here, okay? I like to, okay, I have my cartoon of the orbit is just this curve, okay? It may not be closed, but it's hard to draw. Okay, and then you look on this orbit or orbit closure, you look for a vector that is as close to the origin as possible in this norm coming from the Hermitian inner product. Let's the W. I want to compute W. Actually, the group element giving me W. Or here is the definition. The norm of W, which is I call capacity. This is the capacity. So the problem is this. For a given vector, I want to compute the shortest vector in the orbit closure. Okay. Right. Of course, I can only do it approximately, but I don't formally state this. Then we see there is a connection to this null cone. Well, the vector V being in the null cone just means that the orbit closure gets arbitrarily close to the zero. So it just means capacity zero. Okay. Or if I turn it around, I say V is not in a null cone if and only if I have positive capacity. Okay. Right. Okay. So what we want to minimize is now this function. So I have fixed my vector V. Then the group element G goes to, I hope you understand, G dot V. I just apply the group element in this abstract sense, take norm, and then it's convenient to take logarithm. Doesn't matter. So this is my function FV, the logarithm of the norm of G dot V. Okay, this is the function I want to minimize. Okay, but of course, this group is not a Euclidean space. So but it has nice structure. So what I notice is that, I mean, if I replace, okay, if I do this. Okay. K is in the, let's say K is unitary because it acts unitarily. It doesn't change the norm. So actually my function F here is constant on these cosets. I can view it on the coset space. Don't worry about this notation, but I just say it so that I said it. And this coset space may look very abstract, but differential geometers like it. It's a Riemannian manifold. They call it symmetric space. So there is geometry on it. And actually, it can be a very concrete object. I don't have time to go into it, but for G equals GLN, this coset space can be identified with the cone of positive definite Hermitian matrices. So it's something very concrete, okay, something that people in optimization looked at. So we have a Riemannian metric on it, and we have a notion of geodesics. The geodesics, if I write them for this coset space, they are given by the exponential function. Here is a geodesic. You have a, okay, you are at the point, okay, maybe I can draw it. Oh, here, maybe here's a point G. Okay, naive picture. Then you have a certain direction, H. The direction H, think of a Hermitian matrix, and then you have this function here, which is essentially, it's given by the exponential function. These are the geodesics. And what is very important is this mathematical insight that the function fv is convex. This function is convex along geodesics. So I have convexity. I deal here with a convex optimization problem, but not in a Euclidean sense, but in this Riemannian, okay, sense. Okay, it's convex. This is implicit in a paper by Kempf and Ness from 1979. Okay, good. So this is fundamental, but of course it's not quantitative. So what, okay, here is something quantitative. I put it here. So what can I do? I have, okay, I have my geodesic. Somehow, here's my geodesic again. Okay, gamma. Okay, so I restrict now my function to this geodesic. So I get this function then, maybe I write it here. T goes. Okay, it's a function from R to R. So it's something very familiar to us. I can compute the second order derivative, and then I prove it's non-negative, which proves convexity. But I can also ask in the other direction, how big can it be? And that what is done here, actually, as you see, we upper bound this second order derivative by something. Basically, this bounds the norm of the Hessian, and it's bounded by this quantity 2n squared, and whatever is this n, we call it weight norm. I don't have to define exactly what it is, but think of it as basically the degree of the action, and typically it's quite small. So it's maybe, even for tensor action is free. I mean, it's nothing, okay? So in a way, this Hessian moves only little when I change the base point, which, okay. Right, so I want to optimize. So what do people do in optimization and machine learning? They have gradient methods. So we have to see what is gradient here. Okay, and this brings us to this notion of moment map. So don't worry, it's something really concrete. So I have my function here, and then I take the derivative at the unit of the group. Okay, derivative, and then because I have a canonical inner product, I have a gradient. Okay, this is the gradient, and the gradient I denote mu of v, and it's an element in the tangent space of the group at 1. So this is called Lie algebra. So the mu of v is in the Lie algebra. Actually, it is even in the Lie algebra of my maximal compact group, because if I move along K, I don't change norm. So I mean, it has to go in this direction. Okay, so I have this moment map. So to each non-zero vector v, I assign this gradient of fv, which is an element here. Okay. Okay. Now, if say w, I have a vector w, which is minimal, I mean, as close to the origin as possible, then clearly the gradient must vanish. Okay, this is obvious. But because before I said that I deal here with the geodesically convex problem, the converse implication is true as well. So I have this equivalence. W has minimal norm if and only if mu of W equals 0, which is very, very nice. Okay, very, very nice. Okay, so I just forward you a formula. I mean, now if you know calculus, I don't know, computer scientists maybe don't like it so much, but nowadays they should maybe start to like it. I mean, let me just calculate this gradient, and here it is. So here in the left-right example, so my object is mu A102 AM, and I compute this thing. So what do I get? I get an element in the, I will get a pair of Hermitian matrices. And if I do the calculation, actually of trace 0, because I have SLN, and I get this thing, okay, under some normalization condition. It's like taking sum of squares in two different ways. Okay, yeah. You believe me, just to you see that this is in principle is something quite concrete. Okay, so what do we want to do? I mean, this non-commutative optimization. So there is, it's interesting, there is some duality. I mean, in optimization or linear program, we know duality is probably the most important concept. And here we also have such a thing. It's also in convex optimization very important. And now here we have it again. So by this Kempf-Ness, so again, I have my function that I want to minimize. And then I think dually, I have this moment map, which is just norm of the gradient. And by the Kempf-Ness, I have two problems that are actually equivalent. On the one hand, you minimize the norm, but this is equivalent to saying, yeah, I want to find a point in the orbit where the gradient is 0, and vice versa. So they're completely equivalent. And it's nice to view this. I like to view the left one as the primal problem and the right one as the dual. And for some reason, the dual is called scaling problem. It's because all these algorithms were there already and people talked about scaling. So this is some kind of non-commutative version of linear programming duality. And one thing that we did in the paper non-algorithmically was to develop a quantitative duality theory. Maybe I should mention it, but I think it's important. Just to, let's say, okay, let's say you have, okay, you have a G dot V and the norm is already quite small. Then you would like to infer I'm close to the optimum, but how close? Okay, and this can be turned into inequalities, and that's what we did, okay, in both directions. Right, and then all of this, how does it look like? I mean, our focus is on non-commutative groups, but how does it look like in the commutative case? Commutative, when I say commutative, I mean C star to the N. Okay, there's always this group. And this case is quite well understood in many, many aspects. So the primal problem is unconstrained geometric programming. Okay. The dual problem is called entropy maximation. And yeah, there have been recent papers on that. There's a paper by Straszak and Vishnoi where investigates these problems with the help of the ellipsoid method. I have another paper, a recent one with Lee, Newbor, and Michael Walter, where we, adapt an interior point method for this and analyze it, okay, in the hope that we understand better the general setting. Okay, so this is quite well understood. So, right, now, in the paper, there are two algorithms, the first order and second order. Let me talk about the first order. That this algorithm is just gradient descent. The algorithm is really simple. So what do we do? Right, we are given our vector. Okay. Here again, our problem, we want to find G dot V such that the norm is less than epsilon. Maybe. Yeah. So what we do? We start with G equals identity matrix, and then for a certain number of times, what do we do? I mean, okay, it's inductive, of course. Okay, if you are a W, we compute the moment map. So we compute gradient, compute the norm, and we check, is it less than epsilon? If it's less than epsilon, we stop. If not, we do a step, okay? And that's this step. So basically it means we go in the direction of the gradient, okay, steepest descent, for a certain step size eta that one can figure out, I mean, from what one has to take, okay? And then, okay, we get this result, and this result is actually, let's look at it, it's not hard to prove, okay? So what does it say? Okay, this algorithm outputs, group element, such that blah, 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 norm of gradient less than epsilon. What is the time bound? So here we have, let's look at it. So we have the ratio of the norm of V divided by the capacity and the logarithm. So it's nice to have here the logarithm. Then we have 1 over epsilon square is maybe not so nice, would be better to have log of 1 over epsilon, and then this degree bound, which is usually quite harmless. Okay, so the difficulty is more in applying this theorem. If you want to know something about the null co-membership problem, how can we apply it? So then the work starts. We need to do two things. On the one hand, I mean, one has to prove an a priori lower bound on this capacity. Okay. So we actually prove this. The logarithm of the capacity is this. So, I mean, the capacity can be at most exponentially small. Maybe it's to be expected, but you have to prove it. And that's actually doing this also in this paper on the derandomization. It was the hardest part, that actually Gurwitz couldn't do it because he wasn't aware of this invariant theory. And this is done via constructive invariant theory. So this is the place where the invariant theory comes in. Okay, not for the algorithm, just for the analysis. Okay, no more on that. And in order to understand the quality of the algorithm for null co-membership, we also need an a priori bound, a dual one if you want, on the norm of the gradient. Because, namely, if you have a vector W of capacity 0, then the gradient cannot be 0 because of the Kempf-Nessing is positive. So we have this minimum here, which is a positive number, is a gap, we may call it gap, and we have to lower bound this gap somehow, and it's possible to lower bound it a priori by some quantity that we call the weight margin. Somehow depends on the weights of the representation. No time to define it, but clearly we see when the weight margin is at most inverse polynomial in the input size, we end up with a polytime algorithm. So this is good. Okay. How is my time, Marcus? I'm almost done.
Yeah, so I think there's about 3 minutes left, I think.
Okay, good, good, right. So, good. So I have this slide on the second order, but I will go through it fast, okay? And then open problems. Okay, we have another algorithm, second order, whatever it is. I just wrote the statement. You see, the running time is in a way looks better. What is nice is the dependence on the epsilon is now log 1 over epsilon. Very nice. However, there creeps in this 1 over gamma, unfortunately. So again, this weight margin is the critical complexity parameter. Again, using that algorithm, we obtain polytime algorithm when this 1 over gamma is polybounded. So, so now if you go to these examples or applications that we just have to check what is this weight margin. And then it turns out matrix scaling, left-right action, or more generally quiver actions, they have this nice weight margin, so we get immediate polytime. And this, by the way, is quite nice. What is behind this are totally unimodular matrices. So, I mean, this is a concept that is important in combinatorial optimization. It comes in here in a also quite unexpected way, okay? In the tensor action, unfortunately, gamma can be exponentially small for free tensors. So this is a result of my student Philipp Reichenbach and Cole Franks, based on work by Kravtsov. So, I mean, these algorithms cannot solve null co-membership for tensors. Okay, that's not possible. Okay, this is my last slide. I think I'm in time. There are many, many open problems, a lot of things to do. So as you have may noticed, I really wonder about this null membership for general group actions, especially how about the tensor action. But one can also ask more maybe modest questions, like an intermediate goal would be to prove this is a problem in NP and co-NP. Actually, I thought this is clear, but I was wrong. In the Bloom-Schupf-Smale model, it would be okay, but say, why I think co-NP? Yeah, because of this Kempf-Ness duality, we can have a witness for being at a minimum. But how many bits do we need to write this witness? This is a problem. So it's not clear as in MP, but still, you know, Avi would say morally it should be in QNP. Okay, but we don't know. Then we also notice that, I mean, our first and second order methods, I mean, the guarantees they give, they are not as good as, okay, right. If you think of the commutative case, where I said geometric programming, interior point method, ellipsoid methods give much better results. Okay, and so the question, somehow the idea is, if you want to solve the first problem here, so one direction is to extend this, let's say, interior point methods in some way, or homotopy methods in some way to this non-commutative geodesic setting. So I think that's the biggest challenge. Okay, we know in commutative case is possible. So I think this is, in a way, I think it's the main problem. But of course, other directions is, I mean, not just this null membership. We really want to understand equivalence. So are there polytime algorithms for orbit-closure intersection? Okay, so we recently put a paper on the archive where we proved this is possible in the commutative case, in an algebraic algorithm. Okay, and the last two questions are questions that Avi Viktorson really likes. So, okay, the question is, can these ideas, this complex of ideas, geodesic optimization, lead to new efficient algorithms in combinatorial optimization? So for instance, there is this matching problem, there's the Edmonds polytope. Is it, okay, I didn't show it is a moment polytope, but does it arise in this setting in a natural way, yes or no? That would be very exciting, okay? And finally, of course, I mean, can all these developments, let's say we manage to do it, I mean, does it help for the randomization for the original problem? Does it help for proving complexity over bounds? We don't know, but I think it's a good direction to go. Okay, thank you for your attention.
Thank you, Peter. If people have questions, I think they can just unmute themselves and ask the questions, or if you raise the hand, I'll just look for it and call in order. Yeah.
So there's a question in the chat, right, by Satchapol, which says, could you please mention some applications in the null membership problem in a tensor setting? And the second one, in the Edmonds problem with NBN matrices, if there are only k variables, do we have a deterministic algorithm with f of k poly n time? Assuming that there is an algorithm with n to the O of k time.
Okay, then maybe let's go one by one.
Yeah.
So I think I cannot see the chat.
You cannot see the chat?
Well, let me see. No, I can see it. Okay, I have to open it. Yeah, no, okay, it's fine. No, now I can see it. Sorry. Okay, yeah, just let me go down. Oh, I can read it. Okay, applications to the null membership in the tensor setting. Right. So why this? So actually, I didn't have time, but there is a more general problem. It's the problem of the moment polytope membership, which is very interesting for people in quantum information theory. So there have been several papers. So you have a tensor, and then you can say, yes, okay, you have a tensor, and then we have this moment map. And the image of the moment map, if interpreted in the proper way, is a polytope. And this polytope, people have thought this is a way to measure entanglement. And I think, yeah, that's one way why people are interested in it. I think there was even a paper in Nature or Science, one of the two things. and the null membership is a special case. It's the question whether 0 is in this moment polytope. So this is maybe one possible answer. Okay, and the second one, in the Edmond problem, there are only k. Do we have a? This is parametric complexity. Okay, I have only k. I think I have n by n matrices, but only k matrices, I think. And the question is, do we have deterministic algorithms with a running time fk poly n? Okay, I have to think. I think so. Yes, I think this is true. I think probably one can deduce this just from efficient quantifier elimination algorithms. I think so. Yeah. Yeah. I'm not sure whether it's n to the OK or the n to the O square or something like that, but I think it's true. Yeah. Yeah.
Thank you.
More questions?
There's a question by Joel.
Yeah, thanks. Hi, Peter. Thanks for this fascinating talk. Just a question. So you've been considering all along a group G, and I was wondering whether there's any interest in considering more general objects. In particular, if you have a set of matrices that is, let's say, constructible in the sense of algebraic geometry, but not necessarily a group, and then you view it as a semi-group. And now you can define, some version of the orbit closure intersection problem. Won't necessarily be symmetric if you don't have inverses, but you can define something meaningful. And certainly the null cone membership problem, these sorts of things. Would there be any interest in computing these things?
Well, I don't know. Well, of course, one can investigate all kinds of things, but I think one would need to have at least one example where it shows that this is indeed of interest. So I don't know.
I guess the motivation for this, we recently showed you could compute the Zariski closure of these things, right? And the interest is in it comes a little bit different. But if you look at, say, quantitative automata that are represented by, let's say, matrices, so in general they won't be invertible, right? You have these matrices will not be invertible. Let's say probabilistic automata, various versions of quantitative automata. But you're interested in the closure of what these things can be.
I remember there was a paper, an old paper by, I think, Quaron, Chandel. Is it related to that?
So
it was something related where they computed Zariski closure.
They specifically have groups. Yeah, they specifically group.
They have groups. Yeah,
they have a group of unitary matrices, and the question is, what if you drop this requirement that these matrices be invertible? Right? You just have. But it's not clear that this would have.
I don't know. I mean, but maybe one can do something in that context as well, right? I don't know. I mean, here, of course, we are in a way, from the purely structural point of view, it's something that people studied a lot. I mean, for 100 years. Yes. Okay, but just the quantitative questions and the algorithmic questions are the new things. So I don't know. I mean, when one goes in your direction you suggest, I think probably even the structural thing would be very much open. So
right.
I don't know.
Thank you anyway, Peter.
Yeah, welcome.
Yeah, there's also another question by Charilas.
Yeah, thank you. Thanks, Professor Bürgisser, for the very nice talk. I wanted to ask you something. So when you define this function f, that I believe you prove it convex, right?
Geodesically convex, right? Yeah.
Okay. Oh, and so you had this logarithm there, and then I noticed that in your algorithm you also have some sort of epsilon. So is it like, do you need this algorithm so that you can converge quickly in this optimization problem, or?
Oh, I think, I mean, I mean, it's better. I mean, if you have a function, let's say usual Euclidean setting, you can ask, is it convex or it's logarithmically convex? Logarithmically convex is better. Okay. So, I mean, that's why we take the logarithm. I mean, it's even better. So we prefer to work with the log of the function because it's still convex. And then we can, this helps us in a way. It's like if you think of, if you know geometric programming, it is exactly of this kind. You have a sum. Maybe I can write, but oh, hopla. Let me go to the. I had a free. What did I do? I had a free space, and then I wanted to write. If I have time, I don't know. Okay. Oh, okay, this is tricky. Okay, maybe I write here. So like e to the, now this is a vector. It's in the product. Okay. Okay, this is what. So a function of this. So the w, so x r to the n. The weight is also in, the weights are also in r to the n. So this is logarithmic. This is convex. Sorry, this is convex. Convex. So so what was the? I'm not sure I answered your question, but I had the impression this is relevant. I remember. I wanted to say if you do geometric programming, you say I want to minimize this function, maybe subject to some linear constraints. So that's, and this is a special case of what we are doing. Because what we do, we do a change of variable. I mean, our group elements, like you have a group element. Okay, you write it's e to the something. Now this is maybe something, but then you realize, I mean, what you have here actually, this is not important. Okay, and do a change of variable, and then you end up here. Okay, I didn't have time to do mathematical details. Sorry.
No, thank you.
Okay, so maybe we can take more questions to the gather town. I mean,